guys, welcome to Conceptual Learning. Today we will start a new chapter, hydrocarbons, and first topic of this is nomenclature of alkane and cycloalkanes and their molecular shape, right? So first of all, we will discuss the nomenclature. What is it? Nomenclature is naming, right? So nomenclature is of two types. One is IUPAC and another one is common naming, right? So IUPAC naming gives lot of information. It tells us structure formula, right? But on the other hand, common naming doesn't tell us details of structure formula like that for complex structures. So let's start with the IUPAC naming for alkanes, right? So in this video we'll only discuss some rules and some examples, and on next video I will discuss alkynes and their structures, nomenclature, right? And after that I will upload the video of practice. We'll discuss the names of different complex structures, how to name them, and if names are given, how to write structure formula of those compounds. So now we are starting nomenclature. So first of all we will discuss the rules. Number 1, locate the longest continuous chain of carbon atoms. This chain determines the parent name for the alkane. We designate the following compound as a hexane because the longest continuous chain contains 6 carbon atoms. We use hexane for 6, pentane for 5, butane for 4. We have already learned that in grade 10th, right? So in this example you can see that this is a chain of 6 carbon, so this parent chain name as hexane. The longest continuous chain may not always be obvious from the way the formula is written. Notice, for example, that the following alkane is designated as a heptane because the longest chain contains 7 carbon atoms, right? So it tells us that it's not necessary that parent chain can be straight. It can be bent, right? In this example it is bent, so we will take this as a parent chain, and because it is longest chain, right? So 1 2 3 4 5 6 7, there are 7 carbons in this chain, so this is longest while this is the shorter one because it contains 6 carbons. Rule number 2, number the longest chain beginning from the end of the chain nearer the substituent. Applying this rule, we number the 2 alkenes shown above in the following way. This rule is saying that we will start numbering where the substituent is near. What is substituent? Substituents mean branch. There is branch near from this end, so we'll start numbering from this side, not from this side because branch is far away from this side, so we'll not start numbering from here. We'll start numbering from here. So this is 1 2 3 4 5 6 7, and in this case branch is near here, so we'll start numbering from this side. 1 2 3 4 5 6, right? Use the numbers obtained by the application of rule 2 to designate the location of the substituent group. This is main. Okay, the parent name is placed last and the substituent group preceded by the number designating its location on the chain is placed first. Numbers are separated from the words by hyphen. The systematic names of the 2 compounds shown above will then be 3-methylheptane, 2-methylhexane. How? Let's see. If we start numbering from here, 1 2 3 4 5 6 7, we see that there is a substituent on 3rd carbon, right? And what is substituent? It's methyl radical. So 3-methyl, and what is the name of the parent chain of 7 carbons? Heptane, right? So 3-methylheptane. In another example, there is 2-methylhexane. Why? Because if we start numbering from here, it doesn't matter because longest chain can be this or can be this. 1 2 3 4 5 6, and there is a substituent on 2nd carbon, right? What is substituent? Methyl radical is there, so we will say its name is 2-methylhexane. Rule number 4, when 2 or more substituents are present, give each substituent a number corresponding to its location on longest chain. For example, we designate the following compound as 4-ethyl-2-methylhexane. Let's see. This is a hexane chain. We can see clearly as it contains 6 carbons, and there is a methyl branch on second carbon and ethyl branch or 4 carbon. So its name would be exactly 4-ethyl 2-methylhexane. But why 4-ethyl 2-methylhexane? Why not 2-methyl 4-ethyl hexane? Let's see here. The substituent groups should be listed alphabetically, ethyl before methyl, because E comes first and M comes in the last. In deciding on alphabetical order, disregard multiplying prefixes such as di and tri. This is saying that we'll not name on the basis of di and tri, we'll neglect di and tri when we are naming the compound, right? When two substituents are present on the same carbon atom, use that number twice. Like in this example, 1, 2, 3, 4, 5, 6 hexane is there, and on third carbon there is a methyl radical and ethyl radical. So we will write the name as 3-ethyl 3-methylhexane, right? Because there are two branches on third carbon. So we'll use 3-ethyl 3 for ethyl and 3 again for methyl. Rule number 6. When two or more substituents are identical, indicate this by the use of prefixes di, tri, tetra and so on. Then make certain that each and every substituent has a number. Commas are used to separate the numbers from each other. Like here, we can see 2,3-dimethylbutane. This is a 4 carbon chain, so butane of course, and one methyl is on second carbon and another methyl on third carbon, so 2,3-dimethylbutane, right? We can't write here 2-methyl 3-methylbutane. We will write 2,3-dimethyl because methyl radicals are same. Okay, in this case there is pentane as a parent chain and there's 3 methyl radicals, one on second carbon, third carbon and 4 carbon. So its name would be 2,3,4 trimethyl pentane, right? This is the main one. Let's see what is here. There's butane as a parent chain and there are 4 methyl radicals, 2 radicals on second carbon and 2 radicals on third carbon. So what would be its name? There are 4 methyl radicals, so we'll use tetra. So its name would be 2233-tetramethylbutane. Remember that the numbers would be separated by commas. So its name would be 2233-tetramethylbutane. Now, these two rules 7th and 8th are the applications of the first 6 rules. So let's discuss these. When two chains of equal length compete for selection as the parent chain, choose the chain with the greater number of substituents. This is saying that if you see that in this example 1, 2, 3, 4, 5, 6, 7, if you take this chain, this has 7 carbons, and if you take this as a parent chain, this also contains 7 carbons. So you would be confused which chain you will be considering the parent chain, right? So we'll consider the parent chain which have greater number of substituents. In this example there are 4 number of substituents if we take this as a chain, but if we take this as a chain, right, so there would be only 3 substituents. One will be this and another will be this and last one will be this one. So we'll take this as a parent chain and we'll name accordingly 2, 3, 5 trimethyl 4 and propyl heptane, right? Because they are 2, 3, 5. On 2, 3, 5 position they are methyl and on 4th carbon there is propyl. So is 2, 3, 5 trimethyl 4 and propyl heptane, right? Number 8th rule, last one. When branching first occurs at an equal distance from either end of the longest chain, choose the name that gives the lower number at the first point of difference. What does this mean? This means that first we will see that which branch is near, we will start numbering from that side, right? So in this case these both branches are on equal position if we start numbering from this side or this side. First we'll check for this, then we'll check from which side the branches are more, right? So in this case if we start counting from this side, branches are more near, and if we start numbering from this side, branches are bit far as comparing to this side. So we'll start numbering from that side which has more branches, right? So in this case we start numbering from here because there are two branches, and if we start numbering from here, there is one branch. So we will start numbering from here: 1 2 3 4 5 6. So parent chain is hexane, and there is a branch on second carbon position, third and fifth, and the branches are methyl. So 2 3 5 trimethyl hexane. Okay, so this was IUPAC of alkanes. Now we'll discuss the IUPAC of cycloalkanes. According to IUPAC system, cycloalkanes with one ring are named by prefixing cyclo to the name of the corresponding alkane having the same number of carbon atoms as the ring. For example, cyclopropane, as it contains 3 number of carbon, cyclobutane 4 number of carbon, cyclopentane for 5 number of carbons, right? The substituents are named in such a way that the sum of the numbers is kept minimum. For example, methyl cyclopropane, as there is a methyl branch on cyclopropane. 1,2-dimethyl cyclobutane, there is one methyl branch on first carbon and another methyl branch on second carbon. So it's 1,2-dimethyl cyclobutane. What this actually says that we can't name like that 1 2 3 4, we can't count like that, right? If we count like that, there would be name 1 2 3 4. So there is one branch on first carbon and another branch on fourth carbon, so 1,4-dimethyl cyclobutane. But instead, if we count like this, we will get the minimum number. The sum of the position of the number of branches would be minimum. We will number like that, right? So its name is 1,2-dimethyl cyclobutane. In this case, there is 1,3-dimethyl cyclohexane, parent chain hexane, and there is a methyl branch on first carbon and third carbon, so it's 1 2 3 1 3-dimethyl cyclohexane. That's the IUPAC of alkanes and cycloalkanes. Now we'll discuss the trivial common naming, what it says, right? So it's very simple. We already discussed that it doesn't tell the details, so its name would be very simple. There is butane, as it contains 4 carbon, this contains 4 carbon, so it's n-butane. What can be the isomer of butane? This is the isomer of butane. We can shift one carbon from here to here, so it would become isobutane, right? Its name would be isobutane. Now take the structure of pentane. So this is pentane of 5 carbons. Now what would the first isomer of the pentane? It would be this one, right? And its IUPAC name would be 2-methyl butane. But what its common name? Its common name is isopentane. And if this carbon has no hydrogen and all sides are surrounding a methyl radical, so it's neopentane, right? These prefixes have only limited use as they are not workable with complex molecules, as I already told you. Moreover, common names give you only minimum information about the structure of the compound. Alkenes are similarly named by replacing the ending "n" of the name of alkane with "-ylene", right? So if there is ethene, so its common name would be ethylene. If there is propene, then its common name will be propylene. And if there is butene, this is isobutane, right? Actually, we have discussed this is isobutane. So what would be if there is a double bond? What would be its name? It would be isobutylene. Although it's not in our topic for this lecture, but we are discussing, so there is no issue, right? We are just getting information. Now going towards the structures. What would be the structure of alkane and cycloalkane? Of course, we have already discussed hybridization in first class, right? So there is it, we have already discussed that methanes or carbon with 4 bonds, single bond, have tetrahedral geometry or sp3 hybridization, and all the atoms which have sp3 hybridization form tetrahedral structure, right? So here are some details. The carbon atoms in alkanes are sp3 hybridized and have tetrahedral shapes, with the bonded atoms at angles of 109.5 degree to each other. Free rotation is possible around the carbon-carbon single bonds in alkanes, making the carbon chains very flexible and floppy, particularly for the larger molecules. So the simplest compound here is methane, as it has only one carbon and 4 hydrogen attached to it. But what if the number of carbon increases? Will its geometry be still tetrahedral or will somehow change, modify? Yes, it will modify, right? So tetrahedral bit will change into something 3D structure as the number of carbons increase. But that's not our topic, that's complex, right? And what about cycloalkanes? Cycloalkanes also have alkanes and they have also sp3 hybridization. So at lower number of carbons, they also have tetrahedral shape, but as number of carbon increases, starting number is already 3 as propane is basic cycloalkane, right? So as number of the carbon increases from cyclopropane to decane or something else, so complexity increases and the 3D structures are formed, right? So that's all for this video. Hope you like the video. If you haven't subscribed my channel yet, please subscribe my channel, and if you have any query, please comment in the section below. I will focus on it. Thank you. Goodbye.